Hi, welcome to the presentation video of our work, Closed-Loop Variable Stiffness Control of Dynamical Systems. Dynamical Systems, or DS for short, describe how the system will change in next step. They have recently emerged as a powerful tool for motion generation and task modeling. Typically, as a low-level controller, impedance control would enable the robot to follow the desired motion while ensuring a safe and compliant interaction. With the possibility to vary the impedance parameters, the robot can adapt to different task scenarios and requirements. The traditional way of controlling the robot to follow a desired motion is typically in an open-loop configuration. In such a configuration, the motion generation loop does not have any feedback about the robot state and therefore cannot react to perturbation directly. Thus, the accumulated error from motion mismatch can cause large interaction force to the environment. In this paper, we propose an approach to encode a desired stiffness profile into the first-order dynamical system, which is controlled in closed-loop configuration. The configuration bases on actual robot state, which provides safety and robustness under perturbations or collisions. The proposed dynamical system is built as a weighted sum of springs centered around the wire points generated from an original dynamical system describing the nominal robot motion. The algorithm we propose is that we encode a continuously varying stiffness profile by combining several spring-like linear dynamical systems using nonlinear weight. The linear dynamical systems center around a number of wire points generated from the original dynamical system. Our algorithm consists of 5 main steps. In the first step, we generate a sequence of wire points from the original desired dynamical system. These points build a path from the initial position x0 to global attractor point xn. These points are chosen to have equidistance, which ensures that the velocity profile is smooth. The second step is encoding the stiffness profile. To do that, we construct the constant matrix AI as the multiplication of a direction matrix Qi and an diagonal positive definite stiffness matrix K desired I. The direction matrix is defined according to the direction of original dynamical system. Then we will define the distance-dependent Gaussian kernels and normalize it to be our transfer functions. We will check the sum of Gaussian kernels in real time. Once it is larger than the threshold, which means the robot is far away from the path, a regeneration process will start. This figure shows the effective tube area defined by the threshold. Finally, the VSDS is defined as the sum of the linear dynamical systems, and this DS will be controlled in a closed-loop configuration. Next, we will show the experiment videos of human-robot interaction, collision reaction, and charger insertion to show the advantage of closed-loop control configuration and variable stiffness. We compare the human-robot interaction behavior of our VSDS controller with a classical impedance controller tracking a trajectory generated from the stable estimator of dynamical system in open loop. The setup of our collision reaction experiment is a 7-Dorf KUKA and crash test dummy. The dummy is positioned on the robot motion path to induce a collision. Our VSDS controller is compared with sets in open-loop control configuration. To insert the charger into a socket, the robot starts with a moderate stiffness. Before approaching the socket, the robot increases its stiffness along the insertion direction K1 while decreasing the stiffness in perpendicular direction K2. The figures illustrate the desired stiffness profile.